Hello everyone, my name is Nabil and I'm presenting my group members is ADLAN, MIKAIL, REDZUAN, AL-QAYYUM and Jeffrey. So today we are going to presenting our solution for project 2 gas detector with IoT storage for the subject storage technology and application. So this project is address a critical problem faced by PetroSafe Solutions Sdn, a company that recently suffered financial loss due to undetected gas leak in a storage facility. And our task was to engineer a real-time IoT cloud monitoring system for that detect gas leak and automatically achieve the data into a secure. This is a storage partition which Linux, Debian server, and let's start. And first of all, let's do the hardware layer. We have selected Arduino Mega 2516 as our main processing unit due to its stability and high capacity. And we're going to connect it to the MQ4 gas sensor. We specifically choose the MQ4 because it is optimized for detecting methane and natural gas, which match the petrochemical environment of PetroSafe solution. And for the hardware, we point to the wire to straightforward, and the sensor is a 5V from Arduino, and the analog output is connected to pin A0. Okay, hello everyone. Today I want to show you to connect to the hardware. So we have a Mega 2516 Arduino, and this is MQ4 for gas detector and straight cable and USB type A0. So first of all, we connect to the USB, and for the gas detector, we take a straight cable and find the 3 main for the connection. So first of all, we're looking at A0, GND and VCC, which means volt. So we connected 3 of port in the MQ4. Okay, are we done? And after that, we find the VCC to connect to 5V. So it will become 5V. GND. And A0. Okay, that's it. After that, we plug into the laptop.
After we connect USB 0 to the laptop, we open the Arduino firmware development for the PetroSafe gas monitoring system. The code utilizes the standard Arduino C++ environment running on an Arduino Mega 2560 with an MQ for methane sensor. The firmware begins with initialization. Serial.begin 9600 establishes the communication channel between the microcontroller and our Ubuntu monitoring system. For data acquisition, analog radio captures the raw sensor resistance data from the methane detector. This analog value represents the gas concentration level. The data is then serialized using serial.printgas to prefix each reading, creating a structured packet format that our Python parser can easily distinguish from system noise. This standardized gas value format ensures reliable data transmission. In the Arduino I configuration, we verify the correct board selection as Arduino Mega 2560 and confirm the serial port connection. The serial monitor interface validates the active data transmission stream at 9600 baud, showing the consistent GAS XXXX format required for our monitoring system. This integrated firmware solution provides the foundational data acquisition layer for the complete PetroSafe gas leak detection system.
And the Arduino reads this analog signal, convert to the digital value and transmit it via USB serial. And program the firmware to format every reading as a gas value. This is tagging our backend system can filter out noises and only log valid data. And now we're going to task 2. Let's do a backend infrastructure running into the Ubuntu virtual machine. But first of all, we need to create a hard disk for the SATA, like 2GB for one partition, new partition, like that. So the importantly is connect the USB from the Arduino to connect to the Ubuntu project.
This is the VirtualBox Manager interface. We have set up a virtual machine named Project 2 running Ubuntu 64-bit. The virtual machine has been allocated 5 GB of RAM and multiple virtual hard disks attached via SATA controllers. This setup allows us to simulate a dedicated Linux environment for our gas monitoring project without affecting the host system.
Okay, now let's do the backend infrastructure with Ubuntu storage architecture. For the step first, I want to show you the storage configuration. We have provide and decide a virtual disk for this project to ensure the data acceleration. And first of all, we type ls-blk in the terminal And as you can see here, we have partition name is SDB1. This is mount to specific isolate directly. We create call data guest. This ensure that safely load and keep separate from the main operating system file.
Ever wondered how to create a new partition on a Linux system? Let's walk through it step by step. Here, we are using disk, a powerful command line tool for managing disk partitions. We start by running sudo disk on the device dev sdb. The system asks for the password, then confirms there's no existing partition table, so it creates a new MBR disk label. We type in to create a new partition. We're asked to choose between a primary or extended partition. We choose P for primary, since it's our first partition and we want it to be bootable. We accept the default first sector and last sector, which creates a 2 GB partition. Finally, we write the changes to disk with W, and the partition table is updated. And that's it. A new 2 GB Linux partition is ready to use. Remember to format and mount it before storing it.
SDB1. First, we provisioned a secondary virtual hard disk, which Linux identify as DEV and SDB. We use the fdisk utility to create a new primary partition, SDB1. Once partitioned, we had to format it. We used the command mkfs.ext4. We chose the ext4 file system because it is the industry standard for Linux servers, offering high reliability and journaling capabilities, which is essential for preventing data loss during power failures. Finally, we created a specific directory at data guest. We use the mount command to link our partition SDB1 to this folder. As you can see here, SDB1 is successfully mounted to data guest. We also configured the permission using chmod 777 to ensure our application layer has full write access to this storage.
After that, we open the terminal and type through user mode AT_user to add your user into the dialog group, which is we require to access serial device like Arduino and USB sensor. After that, we restart the terminal and log out. After that, we log back in because Linux only applies permission change after a new login season. When you log in back into your virtual machine, open your terminal and type sudo apt update to update the package list, followed by sudo apt update python 3. To install python 3 for running our program, then install the serial communication library using sudo apt install python 3 serial. And finally, type nanogas_longer.py to open the nano editor where we generate and write the Python script for reading sensor data and logging into the system. That's it.
Section 4, Python data pipeline. There are 3 key configurations here. The first one is port selection. We configure the script to listen on DEV TTY USB 0, which is where the Arduino Mega connects. For the second one, data parsing. The script listens for that guest tag I mentioned earlier. It splits the string to extract the raw integer value. And the last one, timestamping. Using the datetime library, we append a precise timestamp to every reading. The script then opens the CSV file located strictly in our dedicated partition path, data/guest/sensor_log.csv, and appends the new row.
So now, I will run the Python extraction script and first of all, we run a python 3 guest_logger.py. And you can see the system is active and it's connected to Arduino on port /dev/tty USB 0 and listen for the guest tag and mention ED. So wait for a second as data scroll. As you can see, it's capture real data maintenance level and time stepping them instantly.
After we connect the Arduino to Python, the system will start reading guest data from the PetroSafe monitoring setup using the guest_logger.py script. As you can see on the terminal, when guest is detected by the sensor, the data output immediately increases in real time, showing higher values based on the gas concentration in the environment. This proves that the sensor, Arduino, and Python integration are working correctly to monitor gas levels continuously. Finally, once testing is complete, we safely stop the system by pressing Ctrl+C, which halts the data logging process and ends the monitoring session.
Okay, for the step 3 is validation. To prove the data is actually resting in desired partition, and I will stop the script and check the file. And we must stop the script with Ctrl+C, then type cat /data/gas/sensor_log.csv. And here is a proof. We have a permanent log file store the data gas partition containing the timestamp and the gas concentration. And this complete the full pipeline from the physical edge to secure storage cloud
To
storage.
validate that the data is physically stored in the partition drive, I will verify the file content. Here is the proof. This file is physically located on the secondary partition SDD1. We have successfully logged over 10 rows of data, completing the full IoT pipe. For the next section is section 6, challenges and conclusion. In conclusion, we faced a few technical challenges during configuration. The main issue was USB pass-through. The Ubuntu VM initially failed to recognize the CH340 chip on the Mega. We resolved this by installing specific drivers and adjusting the virtual box USB filters. We also had to troubleshoot permission denied errors on the mounted drive, which we solved by properly assigning user ownership to the data/gas directory. Summary of benefits. The system successfully meets PetroSafe need by providing automatic logging, eliminating human error, and data security, keeping logs on.
So, what is the challenge and solution? The challenge and solution is developing the system was not without challenge. The biggest hardest is USB pass-through for configuration. Then the Ubuntu cannot detect the Arduino Mega because the host window machine keep claiming the USB port. And what's the solution? And the solution is we resolve this installation the specific the driver configuration with the machine prior to the Arduino device. And another challenge was permission management. The decided partition was initially locked to the root user, preventing our Python script from writing log. And we solved this by modifying the directive permission using chmod, allowing the application layer to write safely to the storage layer. And and the part 5 is industrial benefit and conclusion. And the conclusion, this system offers significant value to PetroSafe solution. And for the early detection, it will replace manual check which continue 24/7 monitoring. And the second of solution is data integrity. By using a decided storage partition, we ensure that critical safely log assertion and secure. And this system will directly reduce downtime and prevent financial loss, PetroSafe, and prevent inflation. Thank you for watching.
So, as you can see, this is the last video explanation about this topic. It's about industrial benefit. As you can see, the visual is show the industrial benefit image. In conclusion, implementing this system offer PetroSafe solution 4 major benefits. And number 1, it enhances operational continuity by detecting leak instantly to prevent escalation. And then for number 2, ensure regulatory compliance by creating an immutable safety log for audits. And number 3 is enable cost reduction through predictive maintenance based on historical trend. At number 4, the last one is guarantee data integrity by isolating critical record on a dedicated partition. This is architecture effectively address the client need for a reliable, auditable monitoring solution that secure data even in event of system fail. Alright, that's it. Thank you for watching.